right. So today we're looking at the power of products and power of quotients. This is continuing with our exponent laws. Okay. Now I'm also going to bring in some polynomials into this because it's easier sometimes to express these laws with polynomials than just numbers. Now you should be familiar with polynomials. That's when we use variables to express different numbers. So we'll see what that looks like. Okay. What happens when we raise a product? So a multiplication to an exponent, right? So we're looking at the power of a product. And this is basically just a rule about distributing the outermost exponent. But let's take a look. So we're going to start by doing our repeated multiplication. Ideally in the class I would do one or two and then have you guys do the rest. So if you feel like after I've done two, pausing and then trying them on your own and then checking them, that's probably a good way. So if I do the repeated multiplication of this, it would look like so. It would look like 2 times 4 times 2 times 4 times 2 times 4. Now I can rewrite that as 2 times 2 times 2 times 4 times 4 times 4. So if I wrote that as a simplified exponent, that would be 2 to the 3 times 4 to the 3. And my product, therefore, would be, if I evaluate that, using my calculator. Where did my calculator go? It's hiding under these papers. So I would go 2 to the 3, which is 8, times 4 to the 3, which is 64, which equals 512. Okay? But if I wanted to simplify the exponent, I could express it as 2 to the 3 and 4 to the 3. The next one, I have 5 times 3 times 5 times 3 times 5 times 3 times 5 times 3. Now I'm going to gather all my 5s and gather all my 3s. So I'm going to get 5 times 5. Oops, why did I close my bracket? I don't know. Times 5 times 5 times 3 times 3 times 3 times 3. So this would be 5 to the 4 times 3 to the 4. Now to evaluate that, 5 to the 4 is 625 times 3 to the 4, which is 81, which is equal to 50625. Okay. All right. Next one. So I have 6 times 7 times 6 times 7 times 6 times 7. So I'm going to collect all my 6s, 6 times 6 times 6. And then I'm going to collect all my 7s, 7 times 7 times 7. So I would get 6 to the 3 times, sorry, I was going to write a multiplication, but I don't need to, times 7 to the 3. Now I can evaluate that. 6 to the 3 is 216. And 7 to the 3 is 343, which equals 74088. Okay? And then we're going to do this one here. 5, yikes. 2 times 9, 2 times 9, 2 times 9, 2 times 9. 2 times 9, collect them all, 2 times 2 times 2 times 2 times 2 times 9 times 9 times 9 times 9 times 9. So I'll have 2 to the 5, 9 to the 5. Now this might be a pretty big number. 2 to the 5 is just 32, but 9 to the 5 is 5,09049. So I multiply those, and I get 1889568. Woo! Okay. Now, this next one is using variables. And I said we're going to start to incorporate them, which is great because our next unit is polynomials. So it's good to kind of introduce them. So if I'm going to do this 4 times, I will go xy times xy times xy times xy, or x times x times x 4 times y times y times y times y. So I'd get x to the 4 times y to the 4, which is also my answer here. It's my product. With variables, we really can't express it much differently if it's all variables, okay? And then here, I'll have 3xy times 3xy times 3xy 3 times. So I'll get 3 times 3 times 3, and then x times x times x, and then y times y times y. So I will get 3 cubed, x cubed, y cubed. Now for the product, all I can really evaluate is the 3 cubed. So it would be 3 cubed is 27, but the x cubed and y cubed stay the same. Now what patterns do we notice? What we notice is when we move from the original question to the simplified exponent, basically what we're doing is we are moving the 3 in. So the exponent moves to both or all factors in the brackets. Okay, so basically what generalization we can make is that we distribute the exponent to all factors in the bracket. Okay, so if we're writing this out like a rule, basically what we have is, if I have ab to the m, this is equal to a to the m times b to the m. So what happens is this m gets attached to both of those terms in the brackets, and that is our power of a product. Okay, this is our new law. Now, if it's a variable, you can't evaluate it, but if it's a number, you can. So that's kind of key there, right? So this first one would be 3 cubed times 5 cubed, and we can evaluate that. 3 cubed is 27. 5 cubed is 125. So we would get 3,375. Now, the thing with that is that, you really are evaluating, if it's numbers, it might be faster to evaluate it by multiplying in the brackets first, right? So you really want to make a call there, a judgment call in terms of what's going on with those things, okay? And what's going to be easier. So that's why I brought variables in, because variables are where it starts to actually make sense, okay? So let's look at this next one. This would be, now we have a -4 there. Because it's in a bracket, we have to put a -4 in a bracket for our base. Times, so it's -4 to the 5 times 2 to the 5. So the -4 to the 5 would be, let's see, oh, wrong calculator. 4 negative to the 5, it's going to be a negative number, so it'll be -0 or 1024 times 2 to the 5, I believe, is 32, which is equal to, I'm going to have to get squinchy here, negative 32,768. Okay, 8 times 1 to the 4, it'll be 8 to the 4 times 1 to the 4. So it's really just equal to 8 to the 4, right? Because 1 to the 4 goes away, so it's 4096. Over here, we bring in the 3 on both of these, so it'll be negative 4 to the 3 times negative 2 to the 3. And then when we evaluate, negative 4 to the 3, and then times negative 2 to the 3, and we get a positive 512. Okay? Now, again, like I said, it works best with variables. Now, in this case, we also have to remember our power of a power rule, which says we multiply those powers, right? So I'm going to get 4 to the 2, and then I'm going to get x to the 6, because 2 times 3 is 6. I can evaluate the 4 to the 2, it's 16, but x to the 6, that's as far as I can get it. And we use these rules a lot when we move into polynomials, which is why we do exponents before we do that unit. Now, we're going to look at power of a quotient, and we're going to notice that a similar distribution happens. Okay? What happens when we divide a power by another? We divide a power by another power. That's not really the question, though. It's what happens when we well, let's sort it out. I don't even know if that's the right question. So, repeated multiplication here. We would have 5 to the 8 times 5 to the 8 times 5 to the 8 times 5 to the 8. So this would be on top 5 to the 4 over 8 to the 4, right? So that would be our simplified exponent, right? Now our quotient, we can evaluate on the top. 5 to the 4 is 625. And on the bottom, 8 to the 4 is 4096. Okay. Next one, 7 to the 10th, all to the 6th. So on the top, I'm going to have 7 times 7 times 7 times 7 times 7 times 7. And on the bottom, I'm going to have 10 times 10 times 10 times 10 times 10 times 10. So what I would get is 7 to the 6th over 10 to the 6th. And when we evaluate this, 7 to the 6th is 117649, and 10 to the 6th is a 1 with 6 zeros. We know that, right? Okay. Next one, 1 times 1 times 1 times 1 times 1 on the top, and then on the bottom, oops, it's not a 5, it's a 3. 5 times 5 times 5 times 5 times 5. So it's 1 to the 5th over, and I did it again, didn't I? Let's look at this. These should all be 3s. I was so stuck on 5s. 3 times 3 times 3 times 3 times 3. So that's 3 to the 5th. Now 1 to the 5th is just 1. 3 to the 5th is 243. Okay. X to the 4, or x over 4 to the 7th. So I'm going to have x times x times times x times x times x times x times x, that's 7 of them, over 4 times 4 times 4 times 4 times 4 times 4 times 4. So I'll get x to the 7th over 4 to the 7th. Now x to the 7th, because it's a variable, that's as far as I can go with it. 4 to the 7th is 16384. So what patterns do we notice? Well, the base and the quotient stay the same, right? Here I have an x over 4, there I have an x over 4. Base and the quotient are staying the same. Here I have a 7 over 10, there I have a 7 over 10. But the power, or the exponent, is distributed to both the numerator and the denominator. Okay, now what generalization can we make? That we can say that a power of a quotient can be written as the quotient of two powers. Now, I like to write my little rule, so I'm going to write it down below. And again, we distribute, right? I like that word. So we have a over b to the n is equal to a to the n over b to the n, okay? And it's important to note b can't equal 0. So what we're saying basically is that this n gets distributed to both the top and the bottom, okay? So that would be our rule for power of a quotient. It's just about distributing. I am happy to bring in variables because these rules apply when they're variables or when they're numbers. So let's take a look. So this one here, my apologies, we would distribute that 6 to both the top and the bottom. So we'll get 2 to the 6 over 3 to the 6, which is equal to, if we evaluate each of those, 64 over 729. Here we'll get negative 3 to the 3 over 8 to the 3, which is negative 27 over 512. Sorry about the space. It got kind of tiny in here. The next one is going to be 2 to the 3 over 6 to the 3, which is 8 over 216. Now this can be reduced further because 8 goes into 216. So we can also write it as 1 over 27 by reducing our fraction by dividing the top and bottom by 8. Tricky. Next one here. Now the negative sign's on the outside, right? So it'll be negative 4 to the 4th over 5 to the 4th, which is equal to negative 4 to the 4th is 256, and 5 to the 4th is 625. And then the last one here, we have 3 to the 7th over x to the 7th. I can evaluate the 3 to the 7th, and I'd get 2187 over x to the 7th. Okay? Now, these are your exponent laws. Your practice are going to be to finish this booklet. There's 1 and 2 and 3 pages there to work on. Getting used to these exponent laws. They won't take too long, and I will post the key for you so that you can check your work. Okay? All righty.